So we can write equilibrium expressions for virtually any type of chemical reaction. And at this point, you know that a lot of studying chemistry is sort of categorizing different flavors of reactions, whether those are acid-base type reactions. And even within acid-base reactions, we sort of have different flavors of Bronsted-Lowry acids or Lewis acids, etc. And so what we're going to talk about here is really no different than what we've talked about before, except we're just going to apply our knowledge of equilibrium to a specific class of reactions called solubility equilibria, also known as precipitation reactions. So that's when you have ions that come together to form a solid. And in Chem 107, you probably were exposed a little bit to solubility, mostly from a perspective of thinking about generic rules for what is soluble and what is insoluble. And you had a table, and maybe you were given a reaction, and you were supposed to evaluate, is this thing going to be soluble or not soluble, and then write out a net ionic equation for it. Now we're going to give you the tools to never have to think about using a table or memorizing those sorts of things ever again, because we can just compute a K for a precipitation reaction, and then the K literally tells us how much of those ions are going to be present in solution and what propensity the system has to produce a solid or a precipitation. So the specific definition of a solubility equilibrium is really just an equilibrium between a solid and a solution, and that's sort of indicated by the cartoon here, where we have a chunk of solid here on the left surrounded by these water molecules, and this is maybe marking sort of initial condition where you just toss a chunk of solid in, and then it equilibrates, and the equilibrium process is some amount of that solid's going to dissolve, but maybe not all of it will dissolve, right? And we intuitively understand this as how soluble is this. We think about things like table salt as really soluble, so you could put a ton of this in here and the equilibrium is going to lie heavily to the right in this picture, producing a bunch of sodium ions and chloride ions. But there are some salts out there that are sparingly soluble, where you put some in and only a tiny fraction of that solid is going to break apart into its ions. So how do we think about that? Well, sort of generically, we thought in Chem 107 that when you have ions that have larger charges, like +2, +3, or -2, -3, then you have a tendency to have less solubility. And that just makes sense from a simple electrostatics perspective, right? Anytime you have ionic bonds that are being held together by stronger, larger charges, then they're going to be less likely to break apart. But when you have something like sodium chloride, you have just a minus and a +1, and so that has maybe a little bit easier capacity to break apart. This also depends on the size of the ion. So if you have something like fluoride compared with something like iodide, they both are -1, but fluoride is that small ion and iodide is this massive ion, and so the same negative charge is distributed over a much larger surface, which means it's probably a little bit easier for that thing to break apart, whereas fluoride holds on to positive stuff more tightly. So those are the two sort of generic rules he thought about in Chem 107, but hopefully we can connect these concepts, this intuition, with our understanding of equilibrium. So the first thing we have to discuss is there's a convention for writing solubility equilibria, and that's really implied by the name solubility. We're not calling this precipitation equilibria, even though they're linked together. We're talking about solubility, and so solubility implies how much of a solid is going to dissolve. So that means we're always writing solubility equilibria with the solid as a reactant dissolving into its constituent ions. And so the example here is silver chloride, which is a pretty sparingly soluble salt. This equilibrium will be written from a solubility perspective, solid moving towards ions, and we'll be able to write up a K for this, and we call this KSP as the subscript, and that stands for solubility product. And the reason why it's solubility product is because it's written as a solubility reaction, so in the direction of something solvating or being dissolved. And notice when we write out the actual equilibrium expression, which is always going to be products over reactants, and the products of their concentrations, we'll have silver times chloride. And in this case, what do we do with heterogeneous solids, pure substances? They're not included. And so in all solubility products, we're always starting with a solid, which means that the solubility product equilibrium expression is really just a product of their ions. And that's why it's called solubility product. That's the origin of its name. And we can just look this up in a table or Google it, and it turns out that the solubility product for silver chloride as a solid is really tiny, 1.6 times 10 to the minus 10. So all of our intuition at this point still applies, right? What does a small k mean? Well, a small k means that the concentration of these two things multiplied by themselves at equilibrium is this really tiny number. So when you toss a chunk of silver chloride into solution, like this picture here, this cartoon, only a very, very sparing amount of these ions actually break apart, which means that the equilibrium lies very heavily towards the solid, or the reactant in this case. So let's look at a second example here. So calcium fluoride, solid, written in the solubility direction, so breaking apart into constituent ions. See if you can pause the video here and write up a KSP for this solubility reaction. So this is what I came up with. Don't be fooled. Remember, anytime we're writing equilibrium expressions, we might have gotten lazy with our acid-base systems because they were often stoichiometric coefficients of 1. But here, this is 2 fluorides, and we always raise our product concentration to the coefficient for balancing here. So this would be our KSP for calcium fluoride. One more quick example, let's look at calcium phosphate. This is apatite, this is what your teeth are made of and your bones. Let's first see if you can write out the balanced form of this and then the corresponding KSP. So pause the video, see if you can put something together for that. Okay, hopefully you came up with something similar to this. This is a good example of both of these having stoichiometric coefficients here that we need to include as our exponents. So when you're looking at this compound, we've got 3 of these calciums and 2 of these phosphate polyatomic ions. That's what it's going to break up into. And so our KSP is simply going to be the product of those concentrations raised to whatever those coefficients